Hello, everyone, and welcome to this session. I'm really excited to be here. My name is Stefania. I'm a product manager at Databricks. Oh, it's transcribing. Is that?
I think,
okay, I think it's a feature. It's not a bug. So my name is Stefania. I'm a product manager at Databricks, and today I'm presenting with Martin, software engineer at Databricks, and we're excited to talk about Unity Catalog Lakeguard, which is basically how we enforced full data governance for multi-user Apache Spark cluster at the compute level. So as always, this is a product presentation, so product safe harbor statement. So today we're going to start with an overview why data governance is important. Then we dive a little deeper into data governance with Apache Spark, and then we're going to the details of Unity Catalog Lakeguard. So why data governance is important? Why do we care? Today, every enterprise manages large amounts of data, like large data lakes. They're deep. And while they sometimes look smooth and peaceful like this one, there may be kind of dangers around, like sharks, different threats, pollution, maybe even pirates or a monster. So as an organization managing a data lake, you need to ensure that like all the data you're managing is secured so that only the people that need access to the data also have access to it. You shouldn't have like anyone like use your data and potentially misuse it. So that's why data governance is super important. Let's look at the more concrete example. Here with personally identifiable information, PII. This is a very common and also very illustrative example of why we need data governance in the enterprise. In this example, we have customers' data, which consists of names, their birth dates, email addresses, and social security number. So not all of the information is like equally sensitive. Some is more sensitive, some is a little less sensitive. But all of it is PII, and not everyone should be reading that data. So in our example, we have like a team of data engineers that needs to have access to that data. Their task is to ingest, transform, and aggregate data, and for that they need access to the customer's data. So how do you do that? It's by granting them access to the data. So here we grant select on customers to data engineers. We also have a second team. As a result, after granting them select, they can actually query the data. We also have a second team, the data scientists. They don't need access to all of the data in the customer's table. They don't need to have access to the social security number. They don't need the date of birth. So what we can do is remove that data. In fact, the data engineering team has provided a view for data engineers which only contains the kind of data they need for their job. So here we grant the data scientists select on the view so that they can work with that data. As a result, if they select the data, they can select the data and work with it. So in this example, we've used a view to kind of define fine-grained access control. So there's a base table, and over that we want to have a couple of filters to express more nuanced or more fine-grained access controls. There's other ways of how you can achieve this. There's like things like row level and column level filters, attribute-based access control, but all of that is what we call fine-grained access control, which gives organizations the power or the mechanism to reflect their very complex access patterns in terms of data access via the catalog. So now that we've seen why data governance is important, let's have a look at how data governance and Apache Spark work together. So we all know this is the Data and AI Summit. Spark is a super important component of that. Spark is the de facto big data processing framework. And it's also a couple of years old by now. So when Spark was built, it wasn't really built with like data governance in mind. It wasn't built with like some of today's requirements in mind. For example, at Databricks, our customers want to share compute. They want to reduce the costs. They don't want to have like single user, single application scenarios because it's just too expensive, both in terms of like the compute cost, but also in terms of the organizational burden of like managing all these different computes. So architecturally, Spark is has a single VM. There's kind of no decoupling between the application you're running and the underlying engine code. So there's no kind of isolation boundaries like if you run on the same cluster. So let's see what happens when you share a cluster. Here we have our data scientist, data engineer. They're both on the same cluster. They fire their queries. So what happens? We first check permissions. Can they actually access the data? If yes, we fetch the data from the lake. So in this example, the customer's data is fetched from the lake. Now it's on the cluster. So since all the applications run in the same JVM as Spark as the engine, the data scientist could potentially read the customer's data, the data engineer fetched, even though they haven't been granted access to that data. They can only see the customer view. But since we have a shared execution environment, a malicious user may go and actually read that data. So that's a problem. Let's put all the data scientists on one cluster, right? Because then they have the same permissions, like we don't need to bother. They fire the same query. What now happens is the same as before. It's basically, we fetch the customer's table. So why did we do that? So Spark, in order to process fine-grained access control, is actually fetching all the base tables to do the computation locally. This means that if you want to, you could potentially access like the base tables to which you haven't been granted access to. So that's, again, a problem that we need to solve. So in summary, there's kind of two problems if you want to share compute, enforce data governance, and use Spark. Spark doesn't enforce isolation between users and the application. So the governance layer is kind of like the cluster. And Spark overfetches, so if you have this fine-grained access control defined on the table, users can potentially circumvent them. But our users still wanted to share clusters and use data governance, so what did we do? We're super excited to talk about Unity Catalog Lakeguard, which is basically how we complemented Spark to enforce the data governance at the compute level at runtime, so that all the user code would run in isolation and no user could actually read data from any other user. How did we do that? In Databricks, we have two types of compute. We have what we call the shared access mode and the single user access mode. With the shared access mode, we actually went ahead and introduced finer-grained isolation primitives in the cluster architecture, and I will talk a little bit in detail afterwards on like what we did. But we basically changed the underlying Spark architecture to allow us to have a secure multi-user cluster with fully isolated user code. You have full governance, including fine-grained access control. The only limitation is that the data access or the Spark APIs is based on data frame API, which is based on Spark Connect, what we use in the architecture. Not all Spark workloads run on data frames only, right? There's RDDs. Sometimes you want to have like access to the underlying machine. So we also have what we call the single user access mode, which is basically the traditional Spark architecture, where you have like all of the Spark API and you also have access to the underlying machine. We also brought fine-grained access control to the single user cluster, and we'll explain you how we did that in a bit. We first start with the shared cluster. So how did we achieve a multi-user compute in Scala, Python, and SQL while enforcing data governance? We had to kind of solve problem 1 and problem 2 at the same time, like isolate users from each other and also make sure like the overfetching problem isn't there anymore. So we basically had to isolate the users and the engine, and we did that in 2 steps. First, we isolated the client side. We removed or we decoupled the Spark architecture, the server, and the client applications. To do that, we used Spark Connect, which was released in Apache Spark 3.5, 3.4, and which basically introduces a decoupled architecture. So you have a very thin client, and the client communicates to the server via the data frame, via the Spark Connect API, which is based on data frames. Doing that, we actually solved the overfetching problem, because now the user code would run in its own JVM. The Spark server would run in its own JVM, so overfetching wasn't a problem anymore, and we could enforce fine-grained access control. The other thing that we had to do is now separate the different users from each other, so that my user code wouldn't be able to read Martin's user code and vice versa. We did that by basically sandboxing user code, which is notebooks and jobs, so that each user would run in its kind of own container and couldn't break out and read any data from any other user. So as a result, we now have an architecture where users can only read their own data, and we can enforce full data governance with Apache Spark. So now you may ask, what about UDFs? What are UDFs? Not everyone may know, right? UDFs are user-defined functions. It's user code in SQL, Python, or Scala. It's arbitrary code. It may define dependencies. You can use them within a workload, kind of like session-based, or you can even register them with Unity Catalog. And what is really great about UDFs, it's like your way of extending Spark. So you write some code, and it's automatically distributed across all the Spark executors and super efficient in processing. So this is something like a lot of our users use. So now I already said it's kind of, it runs on Spark executors. There's multiple of them. So it's a very similar problem to what we have seen before. So we did something similar to what we did on the client side, where we isolated the user code. On the Spark executor, we also isolate all the UDFs. So there's no sharing of the executor JVM anymore. Each UDF gets their own JVM. We isolate the network access, the host access, and we also make sure that if your UDF defines dependencies, those are loaded into the sandbox. And those UDFs aren't only available on shared clusters, but are also in DB-SQL and DLT. So with all of that, what we now have is a very cost-efficient multi-user compute. You can run it in Python, Scala, and SQL. You get like all the governance, including fine-grained access control. And the API is based on Spark Connect. Very importantly, and this is what a lot of customers we talk to also get wrong, it's because of the naming, and we're going to fix that. You can use shared clusters to develop and also deploy your workloads. You should actually do that because the architecture is different. So you should develop and deploy on the same architecture. And finally, shared clusters are also a foundation for our serverless offering. Serverless notebooks and workflows have been in public preview for a couple of weeks, and they share the same architecture and the same capabilities as shared clusters. The only difference is that this is fully managed. There's actually two differences. Fully managed compute, so it's completely abstracted away from you, like you don't have to do anything with it. And it's an actual distributed architecture. So the client application, the notebook, runs in its own client-side VM and connects to the serverless endpoints. So from that point of view, transition to serverless is super easy. If you're using shared clusters, you can simply move to serverless. If you're using single user clusters, Martin will talk about them in a minute. In order to go to serverless, you need to move through shared clusters. There's also a couple of limitations. I mentioned that a couple of times. As we said, shared clusters are based on the Spark Connect protocol. It's a data frame API, and we don't support lower level APIs like RDDs for arbitrary code execution aren't supported. As a consequence, like all the libraries using RDDs are not supported today, so you can't do distributed ML, you can't do multi-user GPU clusters, and for ML libraries that have like executor-to-executor communication, we also can't support that today. The second aspect is that you don't have access to the underlying machine. So you can't like configure the host machine, host VM. You can't install operating system libraries, compilers, and things like that. However, for customers that need to do that, we have the Unity Catalog single user cluster, and Martin will talk about that.
All right. Yeah, Stefania already said, there are a couple of things that don't work very well on shared classes, and for that reason we have single user clusters. just to recap a little bit, as Stefania mentioned earlier, on single user clusters, we have this problem like, hey, you have privileged access to the underlying machine. So everything in Databricks, for example, if you run a single user cluster, everything runs as root. Running as root essentially means you can install anything, you can like configure, you can mess with your network and whatsoever, which means I can't really provide you with data, with column-based masking, because you can always circumvent that. Like if I'm loading AWS access keys, I can take a heap dump, I can scan through the heap dump to extract these kind of keys. So it's like this, there's like this kind of trust boundary problem. Like again, in Spark, typically the trust boundaries is the cluster level, and single user cluster follows that. And the second part is that on single user clusters, we have this unrestricted Spark API that allows you to essentially do everything. So, but at the end of the day, our customers are still asking us, hey, like how do I share my compute from workloads? Well, because it's expensive, GPUs are not necessarily the most cheapest investment in the world. So they're still asking like, how can we share these kind of computes then? And the other question is, more and more companies and more users are slowly transitioning into fine-grained access controlled world, which means attribute-based access control is important. Fine-grained access control using column masking, row filters is important because we want to enforce all of these kind of primitives at the lowest level in the catalog. You don't want to do all of these kind of extra hoops like in different clusters, different compute types. So for that reason, they're still asking us, how can we solve this? Okay, so first let's start like, how could we actually share a single user cluster? How can we answer this question? And to answer this question, we have to take a step back and look a little bit of like, how our users and how our customers are already using, clusters. Today, when you're issuing grants, which is like a fundamental piece in this architecture, we have two options to issue a grant. You can, for example, say, hey, I grant select on customers to John Doe, or I can say grant select on customers to data scientist. And I think many users start in the first corner, and they say, sure, I add a new user, I grant like select rights to them, and then over time this user switches teams, and like how do you reconcile all of these kind of permissions? And slowly over time they're saying actually like granting to individuals is kind of dangerous because it's like very hard to track and very hard to perform lineage. For that reason, we're saying, okay, we're actually wanting to grant on groups. And if we're granting on groups, then this means there's a subset of permissions that is similar to all of these kind of identities that are accessing the cluster. So what if we let users share a cluster as a group where all of the users that are logging into the cluster share the same permissions? And this is what we are calling the single group cluster. Why single group cluster here in quotes? This is because we're really great at naming things. And so we want to take a step back and say, hey, before we launch this as a product, we want to make sure that we have a consistent story of how you as our users are going to experience our offerings, which means that shared cluster, single user cluster, group cluster, all of these kind of things just like they scream complexity, which makes it hard for you to reason about these kind of properties. For that reason, single group cluster is here in quotes. We're going to come up with a much better name that helps you guide through when is it applicable to use this. All right, so how does it work? Single user cluster today is I have my single user, single cluster, one user, everything is fine. When I'm sharing compute by assigning a single group to the cluster, what happens is that when these two identities logging in to the cluster, their permissions are scoped down to only the permissions of the group, and all of the previous permissions that are outside of the group subset are actually left out at the front door. On a high level, this is very similar to what you know from like Amazon with assume role, So basically, assume role allows you to essentially assume a different identity. The main difference here is that assume role is an identity switch. So you're basically impersonating somebody else. In the group cluster world, you're downscoping. Again, if I use the Amazon equivalent here, is if you're calling STS assume role, you can apply a temporary policy that is applied on top of the role policy. Lots of technical stuff, I know, I'm sorry for that. But essentially, really, this just to show you that you retain your individual identity. So Martin is still Martin, Stefania is Stefania, but our permissions are scoped down to just the permissions that are both of the group that is assigned to this cluster. And what this means is that when you're now when you're sharing this compute, it's guaranteed that all of the identities that are logged into the cluster have exactly the same permissions. And all of these permissions are enforced on the cluster level, and the lineage logging of this principal context is retained, so you know that the identity that was executing an action, and basically everything is owned by the group. And this is perfect, for teams of data scientists that want to share ML compute, like you want to collaborate together on a notebook, on an MLR cluster. This is really perfect for that. And one thing to keep in mind here is that single user and single group are the same access mode. It's really just, I'm using the word single group here because it's like more descriptive than single user or single user group. I mean, like who can reason about that? So again, we're going to fix the naming part, and we're going to simplify the UX with the public preview. If you're interested in this, please feel free to use this magic QR code there to sign up for the private preview. We're really looking for feedback here and to make sure that we're really touching on the things that you care about. All right, problem number 2, overfetching. So coming back to this problem, like now I have my data scientist and I say, okay, well, I really want to read the data from my customer view. And if I do this, then it doesn't work. So like, for example, if you're trying to access a view that you're not the owner of today on a single user cluster, you will get an exception that you don't have permission to access the base tables. Not being accessing the base tables essentially means you can't access this data. The way that we looked at this problem is that we said, okay, how do we provide you with the result data so that you can use essentially the result of your query without processing it on the single user cluster? And for this, we're introducing fine-grained access control that runs on a serverless fleet outside of the cluster. When you're accessing a table that has attribute-based access control, row-level filters, column mask, views, and you don't have permissions to these tables, then we'll basically redirect the fragment of the query, basically the subquery that is relevant, to this filtering service that processes data in a serverless way. It's completely transparent and returns to you only the data that respects your permissions. And the great thing about this is that this is completely transparent. You don't have to configure anything, you don't have to do anything. The only thing that you have to do is enable serverless in your account. Once serverless is enabled and we reach public preview, it will work by default on single user clusters. And you can now finally use row-level column-level masking on single user clusters. You don't need to be worried about this, and we're still going to enforce all of the access permissions. Since the processing happens outside of the cluster, there's a price tag on this, and this work is essentially priced at the rate of serverless drops. So it's at the lower rate of the serverless feature, but it's like giving you access to all of this fine-grained access control data. All right. Usually we end talks with recaps or like outlooks and everything, but we saw this time actually we should like look at recommendations, because what many of our customers are looking for is actually like, how do we do better? How do we understand all of the stuff that we release as a company, and how do we make do with it? And we thought long and hard about this, and it's definitely going to be controversial to a certain degree, but we want to put you on a path forward that allows you to use serverless most efficiently, that allows you to use fine-grained access control without having to think about this. So for that reason, our number one recommendation is, if you're developing something, new workloads, whatever, always try to use shared clusters as your default compute. Again, this is not to say that you should share the compute, this again, naming. This is really just as the architecture of your job that you're using to use the shared access mode. You can still assign, if you have a job, run this as a service principal on a job cluster that runs in shared access mode. It will still be a jobs price and this everything fine. It's really just running this in the same kind of environment with this like full isolation. If shared clusters don't work for you because you're using MLR, you're using RDDs, you're using like very specific things in your architecture, then use single user clusters. And if you're going to single user clusters, then the next big thing is like, please make sure that you're developing and you're deploying on the same access mode. Why is this important? It's like, like when we're teaching, when I'm teaching, my engineers essentially like, how to test, how to write code. Like you always say like, you test the same environment as you run in production. And it's like, how do you avoid regressions? You test the same way as you do in development, in production. And the same is true like for all of the compute types that we're using. So if you're developing on shared clusters today and you're deploying on single user clusters, you're missing out on an opportunity to make sure that you're actually using the same access mode everywhere. And this is really important, to be future-proof, to make sure that you're having the same surface. And once you run on shared clusters, again, as Stefania already said, the transition to serverless is going to be really easy. And with that, we're actually done with our talk. The usual tag, if you have feedback, please tell us what you think about this. And if you have questions, we're definitely happy to answer them all. Thank you so much.